we'll spend quite a bit of time on as to what quantum field theory is, and the special role that symmetries play in quantum field theory. Hopefully tomorrow we'll get to the standard model and sketch it. So the standard model is a quantum field theory. It's an example. And we'll talk about electroweak symmetry breaking. The standard model has a lot, so we could spend a semester or even a year discussing the standard model. I think it's important, since this is the school is about neutrinos, and neutrinos interact through the weak force. It's important to understand the weak sector in particular. So I'll talk about electroweak symmetry breaking, and a little bit about neutrino masses, which to some degree are beyond the standard model of physics. And we'll talk about that. A little bit of reference materials. So I've borrowed. So this is more of a tasting menu of the standard model in particle physics. So to help me pick what to put on the menu, I used some lectures by my friend Yuval Grossman, my fellow countryman, Professor Yuval Grossman from Cornell. For example, he gave many such lectures, but at the Hadron Collider Physics 2016, I invited to give him. I was Javier and he was me. So that's one reference that at least I used. If you want to go a little bit more in depth about quantum field theories in general, I highly recommend the notes by Professor David Tong from Cambridge. He has many fantastic lecture notes about many topics, and in particular on quantum field theories. And that's online, Google it. And the last and very important thing, please interrupt me at any time, ask questions, chat. Javier tells me that somebody's looking on the YouTube chat as well, so feel free to ask a question or make a comment at any time. Yeah, just in terms of the target audience, I assumed you all have learned some quantum mechanics and some sort of analytical mechanics, but not necessarily quantum field theory. But if you have studied quantum field theory, I think this is a good, this is often, in courses, it's often taught somewhat differently. Great. So without further ado, I should not press here, I should scroll here. Let's get to it. So particle physics. What do physicists do all day? What worries us? So here I've tried to summarize it. By the way, this is, if we were in person, I would just have I would write on the board. I think it's easier to follow that way. I'll be writing with a tablet, but I've cheated and I've prepared some slides, but they're only partially full, and then I'll be writing along as we go. What really gets us out of bed in the morning is the question: how does the universe work? Right? What's going on around us? A little bit more specific is, what are the degrees of freedom, and what rules do they obey, right? And in these, the questions about maybe whether there are any new forces, or what is dark matter, and why the Higgs mass, why is it what it is, all of these questions generally fall under these. There are more specific versions of these questions here. So over the last decades, maybe centuries, we've been exploring the universe, and it seems like the language that we've coalesced around in order to understand these questions is something called quantum field theory. Okay, and we search for good models of the universe. Oh, the recording stopped. We search for good models for the universe within this framework of quantum field theory. Recording is back on. Very good. And within quantum field theories, these questions translate at the end of the day to the Lagrangian. What is it? Okay. What does it contain? Right. What's and so the Lagrangian is something that almost any particle physics slide, right, starts with. So let's talk about that, and so the question is, what are the degrees of freedom that appear in the Lagrangian, and how are they organized in it? So let's talk about the degrees of freedom field first, and that's fields. What is a field? Okay, in mathematics, and I'll ask you. Feel free to chime in. I'll open my chat box here. So in mathematics, a field is something that gets a value at every point in space. And in physics, it's also in time. So in physics, what are some examples of fields? Feel free to write examples of fields in the chat. Fermions, electric fields. Fermions we'll get to later. They're the most annoying. Okay, fantastic. So we have electric fields, and we also have magnetic fields, right? These that's one example. The temperature in the room is another. The gravity field. Let's put this. Actually, I don't want to put gravity here. We'll get into physics, just taxonomical discussions here. But there are also other types of emergent fields, like, I don't know, the infection rate of some disease, or the rainfall, et cetera, et cetera. So note that we already have two types of fields here. These are vector fields. And temperature, okay, so long as we don't do very big boosts, this is a scalar field. And probably this one too, right? So they have various transformation properties. Some fields are sort of emergent. So these two happen to be sort of emergent and average quantities, and some quantities are fundamental. Some fields are fundamental to the best of our knowledge. So that's one of the breakthroughs in physics, is the notion that fields are fundamental, and and then you, as somebody in the chat pointed out, they're even more fundamental than we think. Essentially, everything is a field. So fermions, and all the particles we're made of are actually excitations of a field. Fantastic. So these are fields. So let's talk about a field theory. And I'm not going to get to field theory yet, even though that's the header of the slide. Why did I do it this way? Let's talk about, so the fields are going to the dynamics of fields will be governed by Lagrangian. So why are Lagrangians so important? So let's remind ourselves, first of all, before we get to field theory, just in mechanics, what the role of the Lagrangian is. So in analytical mechanics, like the Landau-Lifshitz or Goldstein treatment, we identify the degrees of freedom. Let's call them Q here, because X is going to be reserved for something else. So Q is the thing that we're trying to solve. Maybe it's the position of something, of a particle as a function of time. It's some trajectory. And we write the action. So we're going to use the principle of least action, and the action is an integral from some initial time to some final time of the Lagrangian. The Lagrangian is a function of this coordinate, this degree of freedom Q, but also of its time derivative. Integral dt, and then we minimize. This process of minimizing the action leads us to what we call the equation of motion. That's the equation that we then use mathematics to solve, and we're not going to actually solve anything. But it is well known that this procedure of minimizing the action is equivalent to the so-called Euler-Lagrange equation, which is this beast. This turned out ugly. Right? We take the derivative with respect to q dot on one side, derivative with respect to q on the other. And we, in principle, it's true for all degrees of freedom. So if we basically, if we're smart enough to in solving differential equations, if we know the Lagrangian, we know we probably need some initial conditions, and then we know q of t, right? We know what the particle is doing everywhere. So at the end of the day, this is an exercise in writing down this equation, this function, identifying the degrees of freedom and writing the Lagrangian down. That's sort of the art. As a reminder, the Lagrangian is, loosely speaking, the kinetic minus the potential energy. Fantastic. Good. So now a field theory. So that's what we learned in how to solve mechanical problems. So now we're going to do the same for fields. And the only thing that's happening here is that we're going to promote this degree of freedom from a trajectory in time to a field over space and time. Okay, that's a simple thing. And then often, since we're particle physicists, we are relativistic folk. We like to use this notation of x mu. So that's space and time treated together. You could say that because X became more like time, maybe it should have been called T mu, but nobody does that, except for Yuval, my friend. Good. So now X, no, remember in quantum mechanics, X is an operator. In field theory, X is a coordinate, like time is. So in quantum mechanics, time is a time coordinate. Here X became more like time. It got demoted. Good. So what do we do in field theory? We do the same thing. We write the action. Now it was an integral over time before. Now it's going to be an integral over space and time, because that's all of the coordinates in the problem. The Lagrangian becomes this curly thing, just to remind ourselves that this is a Lagrangian density. It has different units than the Lagrangian in the previous slide. And this Lagrangian is a function of the field, which is a function of coordinates. And it's a function of derivatives with respect to coordinates. And that's it. This we minimize, as we did in mechanics, and we write down this equation, which is again the exact analog of the previous case, only now there are more coordinates to deal with. So it's a little bit of pain in the behind, but that's good. That's fine. We solving equations is the thing we do at the end of the day. Good. So again, solving for how the fields behave in space and time amounts to the question of what are the fields and what is the Lagrangian? What is this function, the Lagrangian? How do they interact with one another? So we will see a few examples. This is field theory, but this is classical field theory, right? We have not done anything quantum yet. Good. Questions so far? Fantastic. Okay. Now it's often it turns out that in quantum field theory we often say the following words, that quantum field theory is just a bunch of harmonic oscillators. And why do we say that? So that's important to realize. And it's not because it's not because we're obsessed with the harmonic oscillator and it's the only problem that we can solve exactly. That is also true. It's one of the only problems that we have sort of a perfect, beautiful analytical solution for. But it's also a really good description of everything. And it is an approximate description. But just as a reminder as to why that is, the field phi will often oscillate around its minimum, right? So the Lagrangian is kinetic minus potential energy. We can also think of it in the Hamiltonian description, which is just there's the plus between them, and there will be some potential energy that will drive the field to its minimum. So here I've drawn I've prepared some field values. Oh, I'm sorry. This is supposed to be all of these fields are supposed to be on the x-axis, and this is supposed to be the potential of the field, right? Okay, so this is becoming ugly, but so I apologize. So this is phi at x1, and this is phi at x2, et cetera, et cetera. And at every space time point, there will be a potential, and it doesn't have to be the same everywhere, right? But it'll be some complicated function, and the why did that happen? And the field will be oscillating around its minimum, right? And so with the so this is whatever this function is, this can be approximated by a harmonic oscillator, right? We're just Taylor expanding. That's all we're doing.
There is a question on the chat.
Yes. Is there a reason to assume that L doesn't depend explicitly on X? It could depend explicitly on X, but in particle physics, it often doesn't. Okay, so I shouldn't take full possession of quantum field theory for particle physicists. Quantum field theory is used by condensed matter folk and by quantum optics people and nuclear physicists. And there are problems where there's some sort of background. There's a nonlinear optics crystal that starts here and ends here. And then the Lagrangian really does depend on X. But as particle physicists, often we think about, oh, what would happen if all of space was very empty and there was only a few particles around, and then it doesn't. So that's just the nature of the problem that we're interested in. Yeah, if it did depend on X, then one of the symmetries that we often take for granted is broken, which is translation invariance, and then we'll get to that. Good, thank you. Good, so this is approximated by harmonic oscillators, and so field theory is just a bunch of harmonic oscillators, right? Right, so here's a potential of Q1, say, and Q2. I said harmonic oscillators, so there's maybe more than one. And same for 2. Let's write this, K2, Q2 squared over 2, and they can be interacting with one another, right? So for example, we can write down a term that couples one harmonic oscillator to the other, right? So this is a quartic term. And if we wrote something like this, I excite one harmonic oscillator and not the other, it will transfer, power can slosh back and forth. We'll get to a slightly different example in a few slides. So that's all of field theory is. It's just approximately, it's just harmonic oscillators. And at least in perturbation theory, if these oscillations become very big, the theory becomes much more complicated, and then we have a harder time. Okay, but so far perturbation theory has proven to be very useful in particle physics. Okay, so I said it's a bunch of harmonic oscillators. How many is a bunch? Anybody care? How many harmonic oscillators did I present when I present a field theory in all of space and time? Any guesses? Should I write numbers? I wrote 2 in the previous slide. Feel free to venture a guess in the chat. Okay, no, one for each dimension. Okay, so that would be 3. Infinite. There you go. This is how many, right? This is an infinite number because at every, right, here at every point in space and in time, there is a harmonic oscillator. And there are an infinite number of points in space and time. So that's a lot. And indeed, for a while in the history of quantum field theory, everything you calculated, the answer came out to be infinite. And it took people a good long while to figure out how the heck they deal with that, but they figured it out. It's all fine. So you'll have to trust me. And okay, so first of all, let's not panic, even though it's the 13th and all that. Yeah, I was going to also, I discovered that I can do this. Yeah, fantastic. Okay, so good. What we'll do now is we will think about, let's think about one at a time. But then so the plan will talk about one quantum harmonic oscillator. Then we'll talk about sort of the infinity of them. Then we'll go back to thinking about 2 at a time because we'll just choose the 2 out of the infinity, and so on. So we'll just get used to it slowly. So that's fine. But it is what it is. It's fine. In one of his lectures about quantum electrodynamics, Feynman, in order to prepare the audience, he told them that yeah, what he's telling them, these rules seem completely ridiculous, and this applies in this case too. But he's sorry. That's what the universe, how the universe seems to be working, and if they don't like it, they can go to a different universe. So, yeah, I apologize. There's an infinite number of harmonic oscillators to deal with. Okay, so one harmonic oscillator. One remark I put it in the corner here is that particle physicists tend to set h bar to 1, also the speed of light to 1. Sometimes h bar will appear here, but so I apologize if the units are a bit sloppy. So here is the Lagrangian for the harmonic oscillator for a single field. Okay, now actually this is not yet a field. This is just phi of t, but because I'm going to go to field theory, I'm already calling it phi. So I'm essentially out of this infinite number of harmonic oscillators, I just picked one. And how do we go about solving the harmonic oscillator? Well, we define the creation and annihilation operators, A and A dagger, annihilation and creation, which turn out to be phi and phi dot. Really, usually in quantum mechanics textbooks, you will get you'll see A is X, so X was replaced by phi in this particular case, plus I times P, right? And it turns out that in the Lagrangian formulation, you don't work with momenta, you work with the time derivative of the field, and P is phi dot. So this is how you define the creation and annihilation operator. So phi is just, can be written in terms of the field is creation operator plus an annihilation operator. And in quantum mechanics, the fact that x and p do not commute translate to the fact that a and a dagger do not commute. They commute to 1. So we write down we solve the theory. We write down the energy, or the Hamiltonian, really. Oh, I changed colors. That's okay. And the spectrum turns out to be particularly simple. The half comes about when an A and A dagger swap places. Here again, H bar appears just for the sake of ceremony, and times H bar omega. So omega is this parameter that appeared in the Lagrangian. So the spectrum is just this evenly spaced, nice spectrum that we get. So this state we call 0, it's the vacuum. It has an energy of a half H bar omega. This is state number 1, 3/2 H bar omega, 2, etc. How am I doing with time? Okay, not bad. So this is all very nice and simple and familiar, and this problem is special because we get this evenly spaced ladder of energy states. So if the reason to think about harmonic oscillators from a couple of slides ago wasn't enough, just the fact that Taylor expanding any potential around its minimum, it's a good the harmonic oscillator is a good approximation. This is also a hint that this is going to be well suited for particle physics, because this is the right sort of spectrum, right? In the sense that for particles, right? As it turns out, so in space, if I think of the energy, let's say I have a particular particle, I can put it in a particular place with a particular momentum, P. I can have either 0 particles or 1 particle or 2 particles or 3 particles with that energy. And that energy is a parameter in this Lagrangian, but in terms of in the language of the particle, it'll be given by the dispersion relation. And for a relativistic particle, this is what it is, right? Again, notice I'm using the word frequency, which is really angular frequency, and energy synonymously because h bar equals 1. P and K are often also used synonymously for momentum and wave number. Right, and putting a particle somewhere, or not necessarily somewhere, but putting a particle in space, it'll be a plane wave, so it'll be everywhere. It's not somewhere. Amounts to applying the creation operator on the state of the vacuum, right? And that will, and another would be another creation operator. So actually the names creation and annihilation operators are much better suited for particle physics, where you actually create and annihilate particles, than it is for the harmonic oscillator, which is, say, a pendulum. So that should make us happy. Good. Questions about one harmonic oscillator? This should be familiar. Good. So now let's talk again about quantum field theories. So this is now phi really is a field, right? It depends on space and on time. This is the Lagrangian. Oh, my handwriting was particularly ugly when I wrote this slide. Remember in the previous slide, we had this term and we had that term. The only difference here is that I changed this omega that was here before to an m, which is the mass. That's because the momentum, the p squared, is captured by this gradient term. So if I expand this thing with the metric, so there's this relative minus sign here. So and that gives me, comes from special relativity. I get this equation, and you already see starting to peak here this combination of p squared, which is coming from this, and m squared appearing here. So I'm not going to derive the solution for you, but it'll look very similar to the normal harmonic oscillator. Remember, in that case, phi was just an A plus an A dagger. Here I will write something similar. So the field in quantum field theory is a sum over momenta. So this is really an integral. I've even wrote this down here. This is what the sum actually is. So this is the infinite part. This is the fact that there's an infinite number of these oscillators. But if I just think about one momentum mode at a time, there's a creation operator like I had here. And what is it that I'm creating? I'm creating something with a particular momentum, which is a plane wave, right? So k mu x mu, right? K mu x mu is just omega t minus k dot x, right? So this is a plane wave. So good. I created and this is the creation operator. There's an infinite set of creation operators to be had, and also annihilation operators, and that creates sort of the quote unquote negative energy plane wave. If I introduce the, hold on, k mu x mu. I'll drop the mu's next time, right? And then the Hamiltonian, which is just the tower of states that we had before, is the same as we had before. It's just h bar omega, a dagger a, but for that particular mode, plus a half. And then there's this trifling little fact that we need to sum over an infinite number of modes, which by now we were alarmed by a few slides ago, but now we're just getting used to it, right? So that's good. Oh, and I should, so every time omega appears here, and omega is the k0 in here, so this is the dispersion relation. So that's what quantum field theory is, at least for scalar fields. For fermions, it's a bit more complicated. We'll get back to fermions maybe tomorrow. Good. By the way, this sum over infinite tower is bad enough for this term, but it's really disastrous here, because clearly we're summing, we're integrating 1/2 over p3k, which will always give, if we integrate all the way to infinite momentum, will give us infinity. So there's a constant contribution to the Hamiltonian that we will just subtract away, and that is a huge fine tuning, and that goes by the name of the cosmological constant problem, which is homework for you to solve. Namely, it's a problem in theoretical physics, and we don't know how to solve it. Great. Okay, so we've stared into the abyss. We saw this infinite set of harmonic oscillators. So far, they are not interacting with one another too much. Actually, not at all so far. In order for them to interact, I would need to add more terms to the Lagrangian. Good, but now let's, again, I have an infinite set of oscillators to choose from. Let's start having some fun with some of them, and let's just pick 2. Okay. And this is going in a particular direction. So here I wrote down the potential for 2 of these oscillators. And so let's, for the sake of simplicity, I picked 2 that have the same frequency. So sorry, in this slide, remember this frequency, the frequency is the momentum squared, the frequency squared is the momentum squared plus the mass squared. If I have several fields, maybe they have slightly different masses. Fields with different momenta and different mass can conspire to have the same frequency. So let's say I picked 2 that have the same frequency, but I'm also adding some interaction term between them, coupling phi1 to phi2 in this linear fashion. So I just pick this 2 out of the infinite set of choices that I have. And now, so what do I do with this term? This is an annoyance. So here's a trick. We can redefine the fields. So I'm going to do a field rotation. This is a unitary rotation in fact, by a 45-degree angle. It's a maximal rotation. And I'm going to redefine these fields into phi plus minus, like so. So now the potential, the new potential in terms of these new fields, and you can check this for yourself. So I'm really just diagonalizing a 2x2 matrix. Even theorists can do that once they consult their notes. So there's a harmonic oscillator for phi plus with a particular frequency. So now the degeneracy between these 2 fields has been broken. Good, and there's no interaction term. So I diagonalized a matrix, so there's no off diagonal term. So I got rid of the interaction by field rotation. We got rid of delta. The spectrum is, it's the same as before. But now different spacing between the 2 fields. I didn't write what the here are the omegas. These are the two eigenvalues. So the two degenerate levels of omega got split by plus and minus delta, and delta is this parameter. So delta is still a parameter in the problem. It's the energy, it's half the energy difference between the two. So what we started off with, what we thought was an interacting theory, and we now have two oscillators that are completely decoupled from one another. So this is not interesting. Or is it? Well, it actually is, so that's wrong. So let's do a little thought experiment that is interesting between these two. I picked, again, two oscillators out of the infinite set that is quantum field theory. And I already alluded to the fact that maybe these two fields have different masses and slightly different momenta, but the energies are the same, right? So this is starting to ring familiar, maybe from yesterday. So let's imagine, just to make life interesting, that I have a source of the particles that are excitations of these fields. And I'm going to, and this is, so here's my source. This is a little cannon here. And I'm going to light the fuse here. There you go. And once the fuse runs out, boom, it spits out a single particle. Right, Javier? That's how you create particles in the lab. And this particle is.
That's correct. Yeah.
Yes, thank you. This is this is a canon of phi ones. Okay, so it only creates phi ones, not phi plus. It creates phi one, which is not an eigenstate of the 2x2 matrix that I diagonalized a second ago. Okay, so at t equals 0, I have I created phi 1, which I rewrote as this. It's a linear combination of the two energy eigenstates. Now at t later than 0, what's going to happen? I'm going to have, let's turn the pen on. I'll have a phi plus. I'll have the same combination and the phi minus. But you know, in quantum mechanics, I pick up e to the I energy times time. So there will be an omega plus here and omega minus here. Good, I can, let's expand this. Okay, a little bit of manual labor won't hurt anyone. So we're going to, because, now why am I doing what I'm doing? Because here at T final, I'm going to have a detector. This is a Skipper CCD that only detects, it's made of specially ordered silicon. And so it only detects phi 2s, okay? Yeah, so I can count the number with 0 readout noise. I can, so Guillermo will tell you all about that. I can detect, but only phi 2s, not phi 1s, not phi plus, not phi minus, phi 2. Okay, so I need to rewrite this back in terms of phi 2. So let's do this quickly. Right, so that was the definition of the phi. Good. And now I can recollect the terms and rearrange this. The answer comes out to be some phase that I don't care about, because I'm going to square this, take the mod square anyway, and when I translate this to probability. And you see, if I collect the phi ones here, I have an e to the I omega plus and an e to the minus omega minus. So the difference of the two frequencies shows up. Back to the pen. So I have the e to the I minus plus or minus e to the I. So that's a cosine of delta omega, which is twice delta, right? Times t, phi 1, and a sine of the same quantity, delta omega times t, times phi 2. Great. So now remember, I have this phi 2 detector here. So in order to calculate the probability of the Skipper CCD showing one electron excited, I need to take the wave function, project it onto phi 2 and square it. That gives me, so that's the amplitude. I square it, I get the probability. And so I can read that off from here. That's just this phi 2 term. The phase goes away. So that's just the sine squared of delta omega times t. So here is the probability as a function of time, going up and down and up and down with this sign. It goes all the way down to 0 and climbs all the way up to 1. So that's interesting phenomena. This is called oscillations, right? And that's one of the reasons we're here today. This is about, this school is about neutrinos. So this is supposed to remind you of Pedro. I think you'll only see Pedro tomorrow, which I'm sure is painful. But Pedro probably showed you. I did not. I would have much preferred to join you guys, but I had something else, somewhere else I had to be. The probability of a neutrino of flavor alpha oscillating into a different flavor beta. This is 1 and 2. This is actually the 2 flavor formula. Is there's the sine squared of twice the mixing angle and the sine squared of a delta m squared L over E. And there's either a 2 or a 4 here. You were there yesterday, so I'm going to put a 2 here and correct me if it's a 4. Please correct me in the chat, or unmute yourself and correct me if I'm wrong. I have a 4 here, but I feel like it's doing. Never mind. Good. So again, these two problems are very similar. In particular, this. No, that's not what I wanted. This term is precisely this term when I translate the fact that, okay, I took equal, there's the question of, are you taking equal momentum or equal energy in your oscillation? And I did this in time and not in space. But what appears here, the delta m squared over 2e, that's exactly the difference in frequencies of two particles that have p squared that obey this relation, right? If they have different, if the difference in energy comes from differences in masses, the difference in frequency is just that. There's also this other term which didn't appear for me. Why didn't it appear for me? How could I, going back to the problem that I set up, can anybody tell me where I could have reintroduced this mixing angle? Or I picked so if you recall, when I set this up, I picked it was actually here. I picked these two frequencies to be similar. I didn't have to do that. I could have had an omega-1 and omega-2. In that case, I still could have done this redefinition, but this would not have been a 45-degree rotation, would have been some other angle. And in that case, what would have appeared here was the sine of twice that mixing angle. Okay, so we've started with just the notion of field theory. We've identified that it's a bunch of harmonic oscillators that can interact with one another. They'll start interacting a bit more seriously in the next slide. And now we already are doing some phenomenology, and we're in fact doing flavor oscillations, right? So once we introduce two fields, we can get this interesting phenomenon. Good. So how am I doing with time? I could skip this and start talking about symmetries, or I could let me quickly go through the process of a decay in field theory. And then we will get to symmetries. So another sort of interesting phenomena that can happen again when we have this infinite set of harmonic oscillators, but when we think about specific problems, often just a couple of them are involved. So here I have two fields. So I already prepared a Lagrangian for you. The fields I have are, again, phi1 and phi2. Now they have different frequencies, right? Actually, this should have been these should have been masses. Mass 1 and mass 2. And finally, I've added an interaction, coupling one phi1 to a phi2, okay? And remember, each of these phis is an A and an A plus an A dagger, with this and decorated by these plane wave factors so you create a plane wave or annihilate a plane wave with a minus in the exponent. So now let's say I start with, now I set off my canon of that creates phi1s. So this is going to be my initial state. Okay, one phi1 of a particular frequency. So now I'm picking one of the infinite set of phi1 operators, applying it on the vacuum, and I have one particle sitting there, or maybe moving. And now what can happen? This guy, through this interaction, can decay to two phi2s. So how does this come about? So and so what really is happening here is we start calculating Feynman diagrams, right? That there will be phi1 Feynman diagram going to two phi2s. But these Feynman diagrams really are just a code for just a time-dependent perturbation theory calculation that we do. So we're not actually going to do that, but let's sketch how that comes about. So I start with phi1 at t equals 0, and then I time evolve it. Again, everything evolves with e to the I energy times time, or e to the I Hamiltonian times time, but I need to integrate that over time. So there's a lot of formalism that goes into this, but the gist of things is that we expand everything. First of all, to first order in the interaction alpha. And we also use this expansion of A's and A daggers. And so from this, we will get, of course, there will be the sum of all of the infinite set of harmonic oscillators in the story. So there's the initial state K1, there's K2, one of the final states, and there's K2 prime, the other final state. There's an integral over space and time. So this is an integral d for x. I'll start at the end of the row here. So I'll pick out there's the because I'm going to act this on phi1. So I'm going to choose the operator that I used to create it, but now I'm going to use the annihilation operator. And then in this interaction that is appearing in the Hamiltonian here, I'm going to pull out two creation operators, right? I'm expanding the phi's in terms of A's and A daggers. So there's an infinite set of terms, but I'm only going to pick one of them out for you. So now I've written down the operators. Each of these operators, as you saw here, comes with their own plane wave factor. So now I need to group those together. For example, the one that involves time will look like this, where delta omega, I did not leave room for this, delta omega is the omega 1 that I took minus twice the omega 2 that I'm going to pick out, right? It's the energy mismatch between the two. There's also a delta k delta function times x. And now it seems like I've left too much room for myself. We can solve that on an iPad. Good. So now you see, first of all, this will take care of that and give me the vacuum again. And then I can, but I can create two particles out of the vacuum. So I will have non-zero overlap with the two phi2 state. So at the end of the day, I will calculate I will sandwich everything like so. So there will be a non-zero term creating two phi1 particles, but it will only be non-zero if these phase factors don't integrate to 0, right? So this is an integral dx and dt, so dx and dt over some phases. And if this integral will go over all of space and time, this will give me 0 unless delta k and delta t are 0, right? So this is going to become the momentum conserving and the energy conserving delta functions. So I don't know if Dario or Matthias Senger are on the line. This slide is dedicated to you, and you know why. But this is particle decay. Well, the reason I brought Darion and Matthias up is because we wrote a paper about nonlinear optics where the mechanics of the calculation is very similar. But you see, so in many cases, even though we start off with this infinite set of harmonic oscillators, we picked a particular initial state. So that's just one mode in a particular harmonic oscillator. And energy and momentum conservation by themselves are going to pick out just the right harmonic oscillators out of the infinitely many that are available in the final state fields that I can go into. So that's already a hint that the infinities in quantum field theory are nothing to be scared of. Good. Questions before I go into symmetries? Okay, again, interrupt me at any time if you have questions. Okay, symmetries are really a key part of our lives in quantum field theory. And so let's again start with examples in mechanics. And switch over to fields. So let's say, just to take an example from mechanics, let's say I have some set of particles, particle 1, 2, and 3, and they have their coordinates. So here's 1, 2, and 3. They have their coordinates R1, R2, and R3. And I'm going to declare that this, the problem that maybe there are some forces between them, and maybe there's something heavy sitting at the origin. So I'm going to declare that there's a symmetry in the problem, which is the rotation around the origin. So I can rotate about this point in whichever way I want, and the physics will be the same. So I can use this to, now, there are many degrees of freedom here, right? So writing the Lagrangian can be tricky, but the trick is to use the symmetry in the problem. And so the Lagrangian will be just a function of all of the invariants, things, the quantities that are invariant under the symmetry. So let's write down some invariants. So for example, if I take R1, this coordinate, this is not invariant under rotation, but if I take the length of this, if I square it, that's an invariant. Okay, good. Same for R2. Okay, that's not interesting. What else can I do? I can take R1 dot and square that, right? So the velocity of particle number 1, etc. Same for the others. Now I can take an interaction between the two positions. R1 dotted into R2, that is an invariant, right? It just depends on the angle between the two, which is invariant under rotations, and the length of these vectors. I can take the velocity of 1 and perhaps oh, sorry, I don't need these beasts here. Any more invariants between 3 vectors? Can anybody think of something that I'm missing here? Okay, if I would have had only 2 vectors at my disposal, I wouldn't there wouldn't be much more that I could do, but this R3 is also around. So if I took if I imagined the parallel pipette, the box that is defined by these three vectors, the volume of that box doesn't change with rotation, and in vector notation, this is another invariant that I can have. And in general, as particle physicists, we often, once we have an interacting system, all of the terms that could appear actually do appear. Maybe some of them are small, maybe some of them are big, and sometimes you would want to explain that. But this is a theory is. We like to say that a theory is natural if all of the terms that are allowed by the symmetry appear. Sorry, I'm sloshing back and forth. Good, Zoom caught up. Okay, so that's symmetries in problems of mechanics. Fields can have so coordinate the position of a particle is a vector. So that under translation and rotation, particularly under rotation, has a very particular transformation law. It transforms like a vector, right? Fields can have non-trivial transformation. So for example, I can have a scalar field. So that is said to have spin 0. An example, can anybody think of an example of a scalar field? Just to show that they exist in nature. Okay, put one in the chat, and I'll come back to you. Okay, the scalar fields that was the last particle of the Standard Model that was discovered was the Higgs boson, right? So that's a scalar field. We have some other non-fundamental scalar fields that we know, more like pseudoscalars, like the pion. We can talk about the distinction between a scalar and a pseudoscalar later. So, okay, we also have spin-a-half particles. So these are fermions. They're weird. So, and the example for a fermion, oh, the slepton. Thank you very much. The slepton is a scalar, but it's hypothetical. We don't know that it exists, unfortunately. Spin-a-half particles. Well, the reason we're here is neutrinos, right? So we must write down neutrino, the electron, the muon, the tau, the quarks, etc. Vectors, of course, the photon, but also the W, the Z, and say the rho and QCD. So these transform as vectors under rotation, and we can go to higher spins. The graviton has spin 2. I skipped spin. There's a number between 1 and 2 that I skipped, which is 3 halves. Andres you in the chat, you may write down the supersymmetric particle that has the gravitino. Thank you. Another particle that may or may not exist, but if it does exist, it has spin 3 halves. It's the supersymmetric partner of the graviton. Good. So unlike the coordinates of particles, fields have have these non-trivial transformation laws under rotation, and that's an interesting story. So when you create invariance, you need to take into account how each field transforms and build invariance, and that's you get the hang of it quite quickly. Fields can also have internal symmetries, right? So the simplest being that I can take the field and I can rotate it by a phase. So this is not a rotation in real space, it's the rotation in field space, so to speak. And the group that's associated with this is U1. And this is an abelian symmetry. So these words are used often by practitioners, so it's good for you to hear them. Or you can take, if there are several fields, I can multiply it by a matrix, often a unitary matrix, in which case the group is SUN, depending on how many fields I have. And this is non-abelian. Abelian and not abelian just means that if I have two arbitrary transformations, they either commute abelian or do not commute with one another. Good. So these are possible symmetries. There are also distinctions between either a symmetry can either be local or global. Okay, if the symmetry is so first of all, what do I mean by that? If I rotate the field, let's go back to the U1 example. If I rotate the field by an overall phase everywhere in space, that's a global transformation. If the rotation depends on space-time, remember it's a field theory, so the field is different everywhere. If this transformation depends on space and on time, this is a local transformation or a gauge transformation. Now, the problem with a gauge transformation is that the kinetic term in the Lagrangian is not invariant. So if I impose it, does that mean I cannot write down a kinetic term? That would be a problem because fields would not, there wouldn't be any dynamics in the problem. But there is a way to make the kinetic term symmetric. So I'll go through this and then we'll see how we're doing with time. So if the kinetic term is not symmetric, well, first of all, the kinetic term, remember, is just this thing squared, right? It's the derivative squared. And as it turns out, that just looking at the derivative, if I apply this transformation, the derivative once will hit the field. So that's this term. And the other term will pull down an I, and there will be the derivative of this theta term times phi, right? So if this was a global transformation, the derivative of theta would be 0, and this term would go away. And then I can just happily square this thing and it'll go away, right? So there's a trick to doing this. You've probably seen this in quantum mechanics when the photon is introduced. So you define what's known as the covariant derivative, which is, I'll go through this very rapidly. I'm defining this derivative, which involved adding a new field, a new vector field. It's a vector because the derivative itself is a vector and it needs to have the same transformation rule. So that's dictated already with what I'm trying to do. And I'm going to declare that this photon, I'm already calling it a photon, this vector field transforms like so. So it doesn't transform multiplicatively like like this transformation here, it's a shift symmetry. So the field, the value of A mu shifts, and it shifts by just the right amount to cancel this beast here. Good. So now, and you're welcome to check this for yourself. The combination d mu phi, now I'm using the covariant derivative, is invariant. So as it turns out, if I want to impose a symmetry to be local, which makes some intuitive sense if you think about it, because everything in life is local, right? If I actually wanted to do a field transformation everywhere in space-time, that would be very hard to, that feels very acausal, right? But if I want to act locally with a transformation, I'm forced to add and introduce a new field. It must be a vector. So a gauge symmetry means that there's a new carrier of force. Good. So that's another important role that symmetry is playing. There is, let's see, how am I doing with time? Javier, what's our schedule for today?
Yes.
Should I pause here and continue tomorrow?
I think, I mean, next talk is Pedro at
Pedro is here.
That's about half an hour after this. So we can stop here for questions and then have a break. That's what our original plan was. So essentially 1 hour and a half each lecture, and then half an hour break for people to drink coffee and do stuff. But yeah, so yeah, I mean, if you have some more things that you would like to discuss today,
I have two slides about symmetry, but let me, I think I'll start with them tomorrow.
Okay, sounds good. Okay, so thanks a lot, Roni. That was
but let me just summarize what we discussed today, and then we can. I'm happy to take questions and give everybody a break for mate. So the philosophy is we want to figure out how the universe works, right? And it's not like the first thing that comes to mind is quantum field theory. It's that the years and decades of trial and error has brought physicists to quantum field theory, but that seems to be the language in which nature wants us to address this problem. And in this language, the question of how does everything work essentially translates to what's the Lagrangian, right? And what are the degrees of freedom? So basically the process is you guess the degrees of freedom, and you think about the symmetries that they adhere to, and then you write down all of the interactions that are allowed by the symmetries. So that's sort of the prescription to start to address this question of how the universe works. And then tomorrow I'll finish off a few remarks about symmetries that are interesting and important. And then we'll talk about the standard model, and the day after we'll get to fermion masses and neutrino masses. Bueno, preguntas.
Okay. Well, thanks a lot, Roni. I have here my mate ready. So
I'm sorry. I'll get my mate in my bombilla tomorrow. Today I have coffee.
Okay, great. So if there are any questions, please, feel free to go ahead and ask Roni. If not, you can always post them on the Slack channel, and we can relay them to Roni, or Roni can answer them directly there. And after the questions, the plan is to have a break of about half an hour, and then we restart with Pedro's talk. Okay, so please, yeah, feel free to ask questions to Roni. Roni is very, very friendly. I can assure you that. So he will be happy to answer any questions.
Sure,
Okay,
I will share my slides. I will put them in a Dropbox, and I will join the Slack channel since I didn't get around to doing that. And I will post it there.
Okay, perfect. Great. Okay, so if there are no questions today, yeah, well, lots of people thanking you for the presentation. But yeah, so if there are no questions today, I think that, yeah, we will surely have more through the Slack channel, and we can continue tomorrow then. So then we have a short break now. Ahora empezamos con un break hasta las 12. Okay. Okay. Thanks, Roni. Thank you so much. That was a really wonderful talk.
Gracias. Hasta luego.
Okay. Hasta luego.
Chao.